Okay, good morning everybody. So today we'll talk about the folded cascade op-amp. So in your homework, you are supposed to find the output voltage range, input common mode range, differential mode voltage gain, common mode voltage gain, input noise power spectrum density at the 10 kilohertz input. And also, you are supposed to find the slew rate, settling time, with those you can find the unity gain feedback with the different values of CL. Yeah, for the slew rate, see, you can change. You need a large step. Like this large step. For the settling time, this is for slew rate. For the settling time, you need a small step. This is input. Yeah, for the slew rate, see, your output looks like that. Something like that, right? Then this rate is V of dV of dt. This max value. That's a slew rate. Yeah, settling time is just this one, right? You can find it is exponential behavior. Exponential related with the bandwidth, right? There may be some constant there. Okay? Yeah, let's talk about the folded cascade op-amp. Yeah, we have a folded cascade circuit. I mean cascade circuit here. There are two pivots in cascade structure. Yeah, this is my PMOS cascade, and I have a NMOS cascade here. So we need a single-ended output. You don't have to write anything, right? Everything will be posted in a home page. So here, see, I have a differential pair here. We'll use also cascade tail current source to improve the common mode rejection. Yeah, this cascade tail current source will improve CMRR. Okay, it will reduce common mode gain. Yeah, so this one is connected to here. See, if this is a VI negative, gate drain, it is negative, then I will put it in positive side here. So from source to drain, the gain is positive, right? Source to drain. Gate to drain, gain is negative. Gate to drain. Yeah, similarly, I will put it like that. Okay. So this should be Vi positive. We can put PMOS input differential pair here. Okay. So let's see, how can I put? Yeah, I have a PMOS cascode there. So, oops. Uh-oh. So let's see, how can I connect it? So this is positive, so this should be Vi negative, same as this node, right? Then this one must be connected to this one. This Vi positive node, this one is connected to that one, like that. Okay. So for the single-ended output, I need this diode structure on the left-hand side of MOS cascode. Okay. Yeah. To reduce noise, to reduce input equivalent noise, we want to operate these transistors in a subthreshold region, which is called weak inversion. Okay, subthreshold and weak inversion. Weak inversion is a kind of the sandwich region between strong inversion and subthreshold. That's in the middle. So sometimes the weak inversion is very effective in increasing gain and also without much sacrificing operating speed. Okay, so we want to operate input transistors in weak inversion, and then those transistors contribute to input equivalent noise. Cascode transistor does not contribute to noise. So we want to reduce GM of those star marked transistors. Then we need to operate them in a strong inversion. Okay? Then see, we already made subthreshold, I mean weak inversion bias for those. We have a self-bias circuit for weak inversion transistors, right? So we can use this one is also weak inversion transistor, a bias circuit like PG1W, PG2W. Okay, those are weak inversion bias. However, for this one, those one, we need a different bias circuit because the same gate source voltage cannot be used for those weak inversion and strong inversion, right? Because they have the same threshold. So for this one, gate source voltage must be smaller than threshold voltage. For this one, gate source voltage must be larger than threshold voltage, right? So we cannot use the same bias circuit. So we need a different self-bias circuit for those ones. So this one connected to PG1S, which is from a different self-bias circuit. Okay, so this is NG2 strong inversion. Okay. Yeah, once we use we get bias circuit from weak inversion self-bias circuit. Yeah, this input transistor works in a weak inversion. It will maximize GM. Actually, this GM is GM1 is related to almost 1 over R, okay, the resistance in the self-bias circuit, all right? Similarly, those GM of these transistors, say maybe GM5, I can say, GM5, I assume this is M5. This GM5 will be also 1 over R in a self-bias circuit. So this R2 must be larger than R1, okay? Yeah, question? Yeah, so let's go back to the self-bias circuit. Question? So question is, how come you apply different bias for this one and that one? Is that your question? Which one? NG2W, this one? What? So actually the question is, see, the difference between weak inversion and subthreshold. That's your question. Huh? Okay, so let's see. This is log ID linear VGS, and then we have some exponential behavior and square law dependence, and then weak inversion region is somewhere around there. That's a weak inversion. It may include a part of this subthreshold region, and then maybe a part of this region, a strong inversion, only a little bit. Actually, I can say for the weak inversion, actually we can divide it something like that. Subthreshold, sometimes the subthreshold includes all this part. Subthreshold includes this weak inversion. Weak inversion, we can say some part of subthreshold region, which flows large current. Okay, weak inversion is the high current subthreshold region. So we can just assume subthreshold region is almost the same as weak inversion. Okay. Yeah. Don't be confused about that. Just they are anonymous. Okay. So let's go to the self-bias circuit. See, what's our self-bias circuit? Okay, our self-bias circuit looks like that. Say we have yeah, then we want to put resistor here. Then let's see, this should be the diode, right? Should be the diode. And then what else? Okay. So this should be also connected to diode, right? So this one is connected to This one is connected to a PMOS diode. Oh, how come it disappears? Small PMOS diode, and then it gets current from this NMOS part, right? And then this thing has also has a small NMOS diode here. And then this gets current from PMOS. So I have some startup circuitry on the right-hand side. We skip startup circuitry. So in the previous case, we have a weak inversion current bias circuit. All the transistor works in a weak inversion. Say we designed all the current flowing through those 4 branches are 100 nanoamp, right? Then we increase the size a lot, like this size transistor 100.7. This is 20 by 0.7, and then this may be smaller, maybe 1 by 2, or I'm not sure exactly, something like that. Okay. So for this large transistor can flow 100 nanoamp current with a very small VGS minus VKH, right? But looks like this is over design. Okay, over design. We can reduce this one something 1 by 0.7 or something like that. It can still works in the service threshold. Yeah, service threshold. Say, okay, so we'll reduce, we'll change this one into some practical design. Yeah, for another assignment, for this one will be strong inversion. Say, this is rather difficult to make a strong inversion operation with this small current. Then I think this should be changed to very large, very small W of L. Like this must be changed something like 1 by 20 or something like that. Then it works at the strong inversion with a 100 nanoamp current. Okay. So to make a self-bias circuit operating in strong inversion, we need to find the transistor size, proper transistor size, right? Okay, question? Okay, let's try simulate this one. Say, where is my Sigma Spice? Open, oh yeah. Here, a line, I have a, service threshold tester. So here, we want to test the service threshold operation.